Good evening, ladies and gentlemen. Today I will be talking about the newest article, which was the issue of conference in uh, international symposium on engineering and sports science in Lazio University. It was in October 2023 conference, and the book is edited by Fabrizio Marinetti, Salman Ali, Remolo Bernardo. Now is published in form of book, conference book. From the title work, which is the cooperation of Professor Della Palcheri, Professor Lenz, and Esposito. And this is with Lazio University, Professor Marco Reis of Napoli University under leadership of Stefano Papirio. The work of Michele Arangiona from Rome, Emilia, and Gawel University under leadership of Professor Pierre Lenz. The work is entitled From Sewage Sludge to Microbial Protein, the role of hydrogen sulfide and carbon monoxide tolerant hydrogen oxidizing bacteria in syngas aerobic fermentation. The work is the anaerobic fermentation of syngas and are generated through the pyrolysis of municipal sewage sludge for the purpose of producing value-added products like microbial protein, holds the potential to open new horizons in biorefinery approaches for wastewater treatment plants. In this regard, in this study aimed to investigate the capability of a mixed community of hydrogen oxidizing bacteria to convert a synthetic syngas with varying hydrogen-carbon dioxide ratios, along with increasing concentration of hydrogen sulfide and carbon monoxide into microbial protein. No inhibition of the enriched culture within hydrogen to carbon dioxide range 2 to 10 was concentration. The question is, how is biorefinery, our hydrogen oxidizing bacteria can work here? And the issue is large quantities of municipal sewage sludge are generated globally each year, resulting in significant operation expenses for wastewater treatment plant and environmental concerns. Pyrolysis allows not only municipal sewage sludge treatment and reduction, but also transforms it into syngas, a gas mixture primarily composed hydrogen, carbon monoxide, and carbon dioxide. This syngas can be to produce like microbial protein. A protein serves as an alternative protein for both feed as well as for the production of biopolymers and slow-release fertilizers. Hydrogen oxidizing bacteria can grow on gas mixture of hydrogen of oxygen and carbon monoxide, accumulating protein concentration of up to 75%. The derived million of tons of gas ferment gases with hydrogen sulfide concentration remains unexplored, while only a few studies have examined few hydrogen to oxidizing bacteria culture to remain unexplored. During the experiments, gas consumption, biomass concentration, yield on hydrogen in demand, equivalence, biomass productivity, and protein content was monitored. The inoculum was for enrichment of hydrogen oxidizing bacteria. The enrichment was conducted in 306 milliliter serum bottles filled with milliliters of mineral barium prepared to a mixture of hydrogen oxide of carbon monoxide in 65, 20, and 15 volumetric ratio was injected in the headspace of each bottle up to the initial pressure of 1.5. The enrichment phase, the fraction phase, periodically diluted and refreshed, achieving a stable growth after 5 weeks. The enriched hydrogen oxygen bacteria culture was then employed in a specific syngas composition. In this first series of match tests, the effects of different syngas were characterized by hydrogen-carbon dioxide ratios of 2, 4.3, 10 hydrogen sulfide were from 2000 to 8000 and carbon monoxide concentration from 10 to 40%. In the second series of batch tests, a 30 days long observation of the effects of carbon monoxide concentration of 10 and 40% and those mixed condition with carbon monoxide 10% volume and hydrogen sulfide of 2000 was conducted by refreshing the gas and liquid phase of each bottle. The short-term batch tests were screening importances of enriched hydrogen oxidizing bacteria culture in the presence of valuable syngas composition, hydrogen carbon monoxide between 2 and 10 in different yields, as well protein content of biomass from 62 to 66% and hydrogen consumption of 87%. Significantly higher consumption was observed for hydrogen carbon dioxide, lightening efficient carbon monoxide. The addition of hydrogen sulfide and carbon monoxide concentration up to 4000 ppm and 40% for the weight, respectively, had no significant impact on the hydrogen oxidizing bacteria from hydrogen sulfide and carbon monoxide on biomass protein content, as well with values varying in the ranges of 39 to 56% in the hydrogen sulfide carbon monoxide, respectively. Long-term batch test concentration as high as 10 to 40% conditions, and the simultaneous exposure to carbon monoxide and hydrogen sulfide concentration of 10% and 2000 per ppm respectively had no negative influence on the process. Biomass yields on hydrogens for carbon oxide was significantly higher, with hydrogen limiting concentration occurring with a tan-wheat plate by mixed composition. The hydrogen-oxygen bond bacteria mixed culture showed a high degree of resistance of hydrogen sulfide and as never reported before the election. The result of this study suggests that mixed hydrogen-oxygen bacteria could derive aerobic syngas fermentation either by directly employing raw syngas with stable process performance and positively influence the costs and technical feasibility of the syngas to power applied to municipal sites syngas management. So that's all for today. Thank you very much for listening to me.